Hello and good morning. So I see lots of people are coming in, so we will wait a little while, a few seconds more to get people in. Yeah. So welcome everyone. We still wait. People are still coming in quite some speed. So we're going to wait a few seconds more so we have more people have logged in. Okay, good morning everyone and welcome to this plenary session. My name is Sofia Feltzing and I will be your chair today. Before we start, I would like to remind the webinar attendees about the housekeeping rules. The session is recorded and will be available later on demand. This is a webinar, which means that you are all who are attending it muted. The panelists, the speakers, are not muted. They can go live and answer your questions. Questions can be posed after the talks or during the talks and after the talk in the Q&A that you find on the plenary session page where you logged in. And those we will select, if there are many, we will select a few after each talk and I will read them out and the speaker will answer them. There is also a Slack channel, which all today's morning speakers are on. It's the plenary's Slack channel of the EAS 2020. And they're all very happy to take questions, make comments, help you understand things after the talks or during the rest of the meeting. Then I have only one small tip for all of you. On the page where you're on, there is also a note-taking facility. This is really handy when you have to save it, and then when you push it out later, it sends you a nice Word document with all your written notes, and it's very easy to take notes in parallel with the talks. I did that myself yesterday, and I encourage people to try it. I think it also accumulates all your notes into one document eventually. With all of that, I would like to, yeah, we're still coming in at a rate, so maybe we should wait one more minute before getting started. Okay, let's get started then. So first up is Phil Diamond. So Phil, if you can unmute yourself and then get your slide up, I'll present you. So Phil Diamond is the Director General at the SKA organization. And today he will tell us about the project and its status. His talk is the Square Kilometre Array, Science, Technology and Status. Please.
Thank you, Sophia. My slides are visible?
Yes.
Okay, and good morning to everybody who's calling in. So I really do wish I was 30 years younger, because astronomy in the 21st century is truly going to have some amazing facilities. Some of the large ones you see illustrated on the screen here, covering the full range of the electromagnetic spectrum. The SKA, Square Kilometre Array, you see in the bottom left-hand corner, will be one of the cornerstones of 21st century astronomy, covering the radio and microwave part of the spectrum. I don't have time to describe in detail the science drivers. There are talks throughout this meeting that touch on the science that the SKA will do, but it's summarized in this one slide here. And it is an enormous breadth of science, covering almost the entire history of the universe, all the way back to the cosmic dawn, soon after the Big Bang, through understanding the origins of life, looking at large-scale structures in the universe, cosmic magnetism, and fundamental physics through testing general relativity and observing gravitational waves. And of course, we're building a facility, so not an experiment. And so there will be new discoveries, hopefully, that the SKA will make. What is it? So it's a global collaboration. We are designing, and next year we plan to start building and ultimately operating next generation radio astronomy observatory. Our international partners have decided to establish a treaty organization, an intergovernmental organization, the SKA Observatory. Just the second such organization in astronomy, the first, of course, being ESO. A little more on that in a moment. We are going to build 2 radio telescopes, an array of dishes in South Africa and an array of low frequency antennas in Australia, with the global headquarters in the UK. And our various governments are working to provide of order 1.9 billion euros, 2020 euros, for the 10-year period, 2021 to 2030, to cover the construction and the first 10 years of operations. Of course, more money will be required after that. This shows the partners in blue on this map. We have 14 countries at the present time. What I'm very pleased about is over the last 2 years, we've had 5 new partners join. You can see their flags on the right-hand side there, and they're all European countries joined the current organization, and will hopefully move across to the intergovernmental organization. On that front, the partners spent a couple of years negotiating a treaty, a convention, we call it, which was signed at a ceremony hosted by our colleagues, our Italian colleagues in Rome on the 12th of March of last year. And 7 of the partner countries signed the treaty. And what I'm very more, of course, are planning on acceding to the treaty in the future. What I'm very pleased about is the Netherlands, South Africa, and Italy have already ratified the treaty, and the other partners there are moving towards ratification. So the telescopes themselves will be on 2 sites. The first is in the Karoo in South Africa, northeast of Cape Town, in the remote part of the country, and very radio quiet, protected by legislation. It's one of the primary characteristics of the site. And I'm sure you're aware of Meerkat, which has been constructed by our South African colleagues, 64 13.5 meter antennas. This is not Photoshop, this is a real photograph of Meerkat, and it's operational and already producing some fantastic scientific results. Across the Indian Ocean in Western Australia, we have the site for SKA Low, which it really is even more remote. It's north of Perth, also a superb radio quiet site. And on this site, our Australian colleagues already have the operational Australian SK Pathfinder up in the Murchison, and the Murchison Wide Field Array, which is a different design of low frequency telescope, both of which are operational. So SKA itself, I can't show you the telescopes yet, although I will show you some prototype systems in a moment. But these are 2 animations of what SKA Low will look like and SKA Mid, as we call them. So SKA Low will consist of 512 stations, each station being 39 meters in diameter with 256 log periodic dipoles in place, each one about 2 meters tall. These will be distributed over 65 kilometers of Western Australia and cover the frequency range 50 to 350 megahertz. In South Africa, moving from 350 megahertz up to at least 15.3 gigahertz, we'll have 197 dishes, which will include the 64 existing Meerkat dishes. So that's what the whole thing looks like. We have a construction period that will start next year and take us through to 2028. We, of course, have much larger ambitions for a subsequent phase of SKA. One of the major challenges that we have in the project is handling the huge amounts of data. So the SKA data flow is illustrated here. You see the 2 low and mid telescopes, which will transmit over fiber optic cables to central signal processors where correlators and beamformers will exist. Huge volumes of data, 7 terabits per second for low, a little bit more for mid. The data from these central signal processors in turn will travel over several hundred kilometers of fiber optics to a supercomputer, one each in Perth and Cape Town. And these are 2 state-of-the-art supercomputers. They will be an integral part of the SKA telescope. The real-time calibration will be done on those supercomputers. From there, of order 300 petabytes per year when we're fully operational, of science-ready data, the science products will be transmitted across undersea fiber optic cables to a network of regional centers, SKA regional centers distributed around the globe. And that's where you, the user, will interact with SKA and take the data products provided by the observatory and turn them into science information and publications. The headquarters sits in the shadow of the Lovell Telescope at Jodrell Bank, south of Manchester in the UK, in that new building that you see in the foreground there. We have a beautiful council chamber and auditorium, which unfortunately we're not using at the moment. But this beautiful facility, the council chamber, has been named after Nani Binyani, who unfortunately passed away as chair of the board a couple of years ago. I mentioned we have prototype hardware on site. This is the dish prototype in South Africa, which is funded by the Max Planck Gesellschaft, but it's a slightly different design from the Meerkat dishes. We've learned from that process. And we're conducting various prototyping measurements and tests using that hardware on the site. And similarly, in Australia, we have a prototype SK low station, which is sitting out there. And this is a joint project between Italian, Australian, UK, Dutch, and Maltese astronomers and engineers who built the prototype station, and we're using it for a wide variety of tests to ensure that we can calibrate these things when we put 512 of them out there. Project like this has significant challenges, as the joys, but also the complexities of an international, a global collaboration. We have members far beyond just the borders of Europe. This has been particularly interesting during the last few months during the pandemic. You have 2 minutes left. Thank you. We have various programmatic issues related to funding, schedule, design, engineering issues, all of the standard, the normal issues that projects have. On top of that, we're establishing a new structure, the observatory, and we're also planning the SK Regional Center network. And then in addition, our friends in the telecommunication industry are launching satellite mega constellations, and we're working with industry to mitigate the impact of these on the SKA. So my final slide shows the overall timeline, which you can see running from treaty last year all the way through to the end of construction. We have achieved that milestone, the treaty signing. We passed the system critical design review. We passed the cost audit. We passed the operations review. Each of them produced recommendations, which we are adopting and fulfilling. The next major milestone, I hope, is the SKA Observatory existing as a legal entity and the first Observatory Council meeting, which is, we hope will occur in December of 2020. So thank you for your attention. I'm very happy to take questions, and I will be at the SK virtual booth this afternoon after lunch. Thank you very much. Okay, so we have, thank you very much, Phil, this interesting talk. We have a few questions, and I start with the first one who came in, which is Sharan Salafia, whose question is, will construction works, for example, at the Cairo site affect the operations of the SKA precursors? The answer is, of course, yes, because if we have several hundred people on site building new hardware, there will be an impact, but we're very well aware of that. We have various protocols and management systems in place which will minimize the impact of the on Meerkat. So these have all been worked out, and of course we'll evolve them as we get on the ground and start the construction activities in 2021.
I have one question from Robert Massey as well, who's asking about the progress on powering the arrays using renewable energy, which he refers to a discussion yesterday where this was a big topic. Briefly.
Yes, so it is our intent to maximize the use of renewable energy for both arrays. In Australia, there is no grid connection. The nearest grid point is about 200 kilometers from the site. And our Australian colleagues already have a 1.6 megawatt hybrid solar power diesel backup system on site, but they're trying primarily to run off the solar power system. We need something about 3 times larger than that, but they have paved the way. So we actually are running an industry exercise looking for solutions there. Okay. And similarly in South Africa, we have grid power to the site, but we really do want to move to renewables as rapidly as possible, because in the long term, we think that will be cheaper, as well as beneficial for all of the other well-known reasons.
Excellent. Thank you very much, Phil. And I'm afraid in the interest of time that could the remaining questions be put on the Slack, because I think they're very interesting questions, and maybe also this one on the renewable energy.
Sure.
So, thank you very much, Phil. Now we're going to move to the second talk, which is by Colin Vincent. So Colin, if you can start sharing your slides. Colin will talk about the new science vision and infrastructure roadmap for European astronomy. Astronet, which he represents, is an organization funded by the European Research Councils. Its original science vision and infrastructure roadmaps came in 2008 and were updated in 2013, and I believe they have been quite influential. Today we will hear from Colin, who is also the chair of the Astronet board, about the ongoing work to develop new vision and roadmap for the 2020s. Please, Colin.
Thank you very much, Sofia. So thank you for the introduction. I will run through this very quickly, as I'm afraid it's a fairly wordy production, but it tells you what we're going to do. So for those of you who don't know, what is Astronet? Astronet is a consortium of European funding agencies with the prime aim of working together to foster ways to improve collaboration, to find areas where there's a common vision, identify common needs. It was previously funded by the European Union, but along with APEC for part of astrophysics, it's now self-funded, funded by the various research agencies, and self-organized. And its intent is to cover all of astronomy, regardless of whether that's ground or space-based, regardless of frequency, facility, or technique. So we have a very broad remit to cover. Who's in it? At the moment, the partners are listed here. Most of these are agencies within those countries: Spain, Belgium, the European Southern Observatory, Hungary, Netherlands, Sweden, UK, and Italy are all members. And we have observers from the European Space Agency, the European Astronomical Society, the SKA, and the Council for German Observatories. And we have strong connections at the moment with APEC, with the European Union networks, Opticon, Radionet, Solanet, etc. So we are trying to reach out to the community in as many ways as we can. Astronet is the only body that's produced so far and updated a single vision for European astronomy. And we think that has been a very useful and a very informative document in the past. We believe it was highly recommended by the European Union, or highly regarded by the European Union. It became a scientific reference for the European astronomical community. And it was very influential, we believe, in many countries in terms of their support and engagement with big projects like the European Extremely Large Telescope and the SK, as we just heard from Phil. It's also been influential in forming consortia to address some of the common instrumental needs, such as WEAVE for the Isaac Newton group in the Canary Islands. And it's fed into national strategies, and we believe in some cases helped some people show that they are part of the wider European initiative for astronomy. So as I say, it's been quite an influential document, we believe. But that was all several years ago, and science and the political position and the financial position has all moved on since then. There's been new European S3 roadmaps. There's been discoveries such as the working gravitational waves in fast radio bursts, exoplanets, etc. And so we really feel there's a need to have a new European view now, one that looks forward to the next few years and to all the exciting things that happen, some of those which you saw on Phil's slides in the previous presentation. We need to look forward also to the next generation of space missions that ESA is considering through its Voyage 2050 exercise, and other areas which are higher profile. We just heard about the environmental aspects of the SK. There's environmental aspects of all of the work that astronomy does, which we need to take into account and have an idea of how we want to work with that, and looking at sustainability of our science, of the community, and that includes training, and of course the aspects of computing, artificial intelligence, etc., which are becoming much more prevalent now. So that's the why. How will we do this? Led by the Astronet board, we wanted to keep the process as simple as possible. And that means we were going to combine the science vision and infrastructure roadmap into a single document. And we're not going to have white papers. We're going to have a number of panels which will do the work. Previously, there's been a single leader for this exercise. This time we wanted to have the leadership come from the panels themselves, along with the Astronet board and other people helping, but a much broader team. And of course, we wanted those panels to represent all areas, but also to take account of being gender, experience, and geography relevant. And the inputs and outcomes, we want to be representative and consensual. We don't want anybody to feel that they're left out of this process. The panels have been created, and they're covering big science questions. Some of these you will have seen from the previous Astronet Science Vision and Roadmap, but they're ones that I'm sure everyone will recognize because they're very broad and meant to cover the broad areas in as few panels as we can cope with, but not again to be exclusive. And what are the panels going to do? Well, we hope that they will provide a broad description of their own remit, their own scientific area, and the interdisciplinary aspects of those, the current strengths of the European community in those areas, the status of the field, and a vision of what's needed next, both in terms of the science questions and the key issues, but also then the facilities that are going to be needed over the next 3 to 5 years and out to the next 20 years. And this will give us a real view and a real feel for what we're going to do and what we hope to do next. And we want to see what the leadership there is for Europe in these facilities. It may not be that all of these are going to be led by Europe, but we want to see what the role of Europe may well be. And there's going to be some missing capabilities, things that currently we don't have, or that are becoming more important as the science moved on. And I mentioned time domain science here as just one example of something that's grown a lot in the last few years in terms of its importance. And of course, with the exploration program that ESA and other space agencies are leading, there'll be need for looking at sample return, we hope. There's also skills and training, as I mentioned before, and we have a huge number of areas of overlap between what is core astronomy and the other areas which are very much related to astronomy, particle astrophysics, the whole working gravitational waves, cosmic rays, dark matter, neutrons, etc. We need to make sure that we are joined up with the rest of the areas of science that we work with. When do we hope to do this? So we had a kickoff meeting of the panels in April, and they're all formed and working. You can find the membership of the panels on the Astronet website, and I can point you to that later. And the timetable going forward now is that we hope to have some drafts, initial drafts of the text that those panels will produce by September, October. As I said, we're looking to move this along fairly quickly. We will then have a community consultation through November and December and look to finish the process in early 2021, around the first quarter. And in common with other international strategies, we would hope to present this to the agencies, to the wider community and to the EU in the first part of 2021. In the same manner as we've just seen the particle astrophysics community delivering their strategy, and of course a while ago the astroparticle physics community did for their community. So we're looking to do the whole process fairly quickly, but there will be an opportunity for the whole community to get engaged. And indeed the panels themselves are now reaching out to make sure that they have the coverage and expertise that they need to do the work that we've set them. So this talk has been really to set out what we're doing, to show that there is an opportunity for people to engage with the process, and that there is the panels and the Astronet board are working already in order to get it underway. I'll just leave you with the two contacts, my own and the Astronet web pages, where you'll find both more information, and you can contact me if you want to get more information directly from me. Thank you very much.
Thank you very much, Colin. So we have a few questions here, and I think we can cover some of those in the time allotted. We will start with the first one that came in by Paul Cohen. Is there no concern that some research that does not easily fit into big science questions will fail to be funded in the future?
There is an opportunity there for the panels to be as widely based as possible, and they'll be looking at all areas of science. So they're not just looking at the big science there, they're looking at all issues, and they will take account of the range in scale of things that they will do. For one example is that they will need to prioritize facilities and science in their report. And one of the issues they're looking at there is scale, to ensure that they're not just focusing on the big issues or the very big science facilities, but also taking account of the smaller issues and the small communities that their voice also needs to be heard. Thank
you. Then we have Jakob van den Einden. Things are moving around in this question thing somehow. He asks, he says, thank you for the interesting talk. You mentioned area with a high profile. I was wondering if there are also efforts to increase support, diversity and inclusion within the European astronomy. I think that's one of the areas that the report will definitely cover. Of course, this is a report to the funding agencies, so we have no power. We can only report and make sure that the issues are made widely aware. People are made widely aware of the issues. But yes, the panels and Astronet are very much aware of that. And I'm sure that will be one of the interdisciplinary, the cross areas that every panel will want to make sure is included and highlighted to the funding agencies and to the European Union. Then we have Robert Massey asking the question, will the UK remain in Astronet after Brexit, particularly if we leave Horizon? As I said, Astronet is funded by the funding agencies, not the European Union. So it's an independent organisation. So the fact that the UK may leave Europe, Brexit, will not have any effect on Astronet at all. Very good. Then I have two remaining questions, which I think we have time to well, I would like you to address Connie Ertz's question in the Slack channel afterwards, because she says, perhaps say how we plan to consult the community in the fall, and maybe we can address that in the Slack, which is already going nicely with lots of SKA stuff. And then Leo Butcher asks, can you say how the challenge of the climate crisis is driving your discussions about the science vision for Europe? For example, we will not be able to rely on massive flying or non-sustainable electric power very soon. Yes, so I did mention that the environmental sustainability generally of astronomy is one of the issues that has emerged as a high priority over the last few years. And we've already told the panels that that is something that we will need to address. And we'll probably have a separate section in the report that will cover the wide range of issues that come under that sustainability and environmentally sensitive remit. Okay, so now Colin, I see that the Slack channel is already popping up lots of more questions for you. So thank you very much. And thanks everyone for engaging with such interesting questions. Thanks. And then we will move on to the next talk, which will be by Serena Viti. Hello, Serena. She will talk to, so Serena Viti's research focuses on the field of astrochemistry and the study of molecules in space. She has previously served as the secretary of the EAS, and so it's particularly a pleasure to introduce her here today. And she has also won an ERC Advanced Grant. Recently, she moved from the University College London in the UK to Leiden Observatory in the Netherlands. And today, she will talk to us about characterizing the dense gas in starbursts and AGNs, a journey into the molecular content of nearby galaxies. Please, Serena.
Thank you very much, Sofia. I assume you can all see my slides. Well, first of all, I'd like to thank the Scientific Organizing Committee for inviting me to give this plenary talk. Of course, I would much rather be there in person, but hopefully there'll be no problem, no technological problem with this talk. So as Sofia said, I'd like to give you a short talk on the importance of characterizing the dense gas in starburst and active galactic nuclei, or in other words, I would like to take you for a short journey into the molecular content of nearby galaxies. But before we start, I like to make sure that I personally acknowledge and thank previous members of my group as well as the present group for all the help and all the great work that they've done. And without them, all the science I'm going to talk about would have not been so much fun to do. Okay, so let me start with the big picture first. What are the main questions, or some of the main questions, in galaxy formation and evolution? Here I list just 4, but of course you may have your favorite ones which are not necessarily represented here. The 4 ones that I want to just mention, and obviously I'm not going to answer them during this talk, are what are the physical processes that drive star formation in galaxies, in particular in nearby galaxies, which is what I'm going to concentrate on today. Many galaxies, maybe all, have an active galactic nucleus in the center, and we are very much interested in understanding how AGNs are fueled. AGNs, of course, affect the surrounding interstellar medium, but how they affect the surrounding interstellar mediums is still a very hot topic. And finally, of course, galaxies interact energetically with the intergalactic medium, and there are, in fact, several talks during this EAS meeting that covers this particular topic. So, my next question is, how can we help? Or in other words, how can astrochemistry help? And maybe this little 4 panels cartoon here can give you a hint on how I think molecules, or understanding molecules, studying molecules, can help answering some of the questions that I posed in my previous slides. So these 4 panels, of course, these 4 nice pictures are taken from our own galaxy and represents an extremely simplified view of a multi-million-year cycle of star formation, or what happens to the gas, to the molecular gas, starting from the diffuse gas there on the left-hand side, diffuse translucent gas that is, although UV penetrates in this gas, you still have some molecular chemistry going on, and many molecules, in fact, have been observed in these regions, moving on towards those dark places where stars will form. There the temperature is low, the density is starting to be high, and molecules form both in the gas phase and on the surface of the dust. Once the stars, or the clusters of stars form, of course the gas and the dust surrounding them will start heating up. And eventually you have beautiful jets that come from, arise from the stars, which are still cocooned in their dust shells. And although this happens in our own galaxy, I think you can scale it up and see that similar processes, similar energetic processes will go on and are going on in galaxies. Up to, in fact, to large scales outflows, which, even if I don't resemble these small jets that I'm showing here, still will share similar processes. And so really my point, my take-home message from this slide is that molecules can trace all these different processes. They can trace the dynamics, the physics, and of course the chemistry of the dense gas in all these regions. And due to the intrinsic spectroscopic characteristics of molecules, you have a different molecular species in different abundances may trace different gas components, as well as the different evolutionary stages. And so, and here is a hint of really my main take-home message, is that if you have different transitions of different molecules, then you for sure will trace not only different gas components, but also different excitation conditions. However, before we move on to show you what excellent science you can do with molecules in nearby galaxies, it's fair to first point out the challenges that astrochemistry, when applied to extragalactic environment, will have to face. The first one, and that's the one I'm going to concentrate during the rest of the talk, is that even for the closest galaxies, M82 and GC253, the spatial resolution even of the best instruments such as ALMA, will encompass, it's likely to encompass few parsecs of gas. And as we know from galactic studies of molecular astrophysics, few parsecs of gas will encompass emission from an ensemble of multi-phases gas, where you have a mashup of both spatial and temporal effects, both diluted in the same beam. So this is our first challenge. The second one, which I will mention, but we will not touch upon for the rest of the talk, is this one. I couldn't help putting this slide on. The second challenge, but it's also a positive challenge, is an exciting challenge, is that molecular spectra of nearby galaxies now are certainly as rich as the ones in the Milky Way. This is a wonderful preview of a paper in preparation led by Sergio Martin and the Alchemy collaboration. Alchemy is a large ALMA program, and this is a spectrum from the nucleus of NGC 253. And I think it's suffices to say that even if you don't manage to read all the labels, it's clear that the spectrum is super complex. So we're looking forward to interpret such spectra in nearby galaxies. Going back to the first challenge, how do we overcome the challenge of large beams? Or in other words, can we still find key molecular transitions, key molecules that can unambiguously trace individual physical and energetic process in active galaxies? So indeed, many have proposed before that we can use particular molecules or ratios between two molecules to trace different processes. Here I'm just putting an example. One of the most used ratios is the ratio between HCN and HCO+, that both, for example, here I've got two examples of two galaxies, NGC 1068 on the left and NGC 40389, or in other words, the antenna galaxies on the right, where it seems that HCN is higher in the nucleus than in the overlapping regions for the antenna galaxies or the starburst rings for the NGC 1068. And so often, this therefore has been used or has been proposed, this particular ratio has been proposed as a signature of the AGN activity. However, other studies show that in fact, there is no enhancement of HCN or HCO+ in the nucleus of galaxies. So here I'm just giving you an example from a relatively recent paper by Nanase Arada and collaborators. And she essentially finds that the intensity ratio of the 1:0 line, HCN over HCO+ 1:0 line, is basically the same and it doesn't differ. In a more recent paper by George Privan and collaborators, they looked at a sample of galaxies, and when they studied statistically the HCN over HCO+ ratio, as you can see here on the left-hand side, and when they plotted it versus the luminosity, the ratio of the luminosity of the AGN over the infrared luminosity, we find that really they could not exclude a null correlation between this ratio and the luminosity of the AGN. On the right-hand side, this is also shown using a chemical model, which is showing the HCN over HCO+ ratio for various conditions. So the colors there are the different gas densities, while the squares, crosses, and rounds are for different cosmic ionization rates. And on the y-axis, you've got the different transitions of these two molecules. And what this plot is showing really is that this ratio can vary quite a lot, both with time, which is on the x-axis, and with different conditions. In a less pretty way, this is also, this is also shown with this plot here. Again, you just see random squares, and what you're seeing here is the ratio of HCN over HCO+ as a function of different chemical models that have been run, ranging those conditions there that you can see in the middle. So large range of gas densities from 10 to the 4 to 10 to the 6 per centimeter cube, a large range of cosmic ionization rates from galactic to 500 times the galactic one, and so on. And really what, again, the takeaway message there is that those spots there are rather random. And basically what this is showing is that very different chemical models may give very similar line intensity ratios for these two species, and vice versa. So how do we still use molecules despite these challenges? Well, we need really a systematic methodology to interpret molecular observations and molecular line ratios, especially in galaxies where the beams are large enough to encompass multiple gas components. So in this little flow diagram here, I'm just showing you how one ideally should approach the interpretation of molecules. But really, again, as often the message is, you really need to obtain as many lines and as many transitions and as many molecules as you can at the same spatial resolution. And then an interactive and iterative process between the observations, radiative transfer modeling and chemical modeling will actually lead you to be able to disentangle the degeneracies and the challenges that I've mentioned before. And so I'd like to take this opportunity to advertise one of the many chemical codes that are out there that can help you solve these problems. So this is a code that has been developed by my group over many years. And here on the right-hand side, you have the names of the people who are maintaining it at the moment. It's an open source code. GitHub is extremely modular, and I don't have the time to describe it here, but please do ask me if you're interested. It's very easy to use, and I hope that many will use it. And now they've introduced you at least one of our tools. I'd like to spend the remaining 10 minutes or so showing you an example of how we apply the methodology that I've just mentioned in the previous slides to a very interesting galaxy. This is NGC 1068. It's a Safer-2 composite galaxy, so it's got an AGN in the middle, and it's got a beautiful, two beautiful starburst rings. This is a galaxy that is studied, has been studied by many people, not just by us. There are many works that I refer to, some of them at the bottom of the slides. And the work that we've been doing on this galaxy, over the years, has been in collaboration with many people, which again, I list most of them here on the right-hand side. So what I'm going to do now, I'm just going to pick and choose a few molecules and show you what we've been doing with these molecules for this particular galaxy. And I'm going to start with CS because this is a paper that just literally been accepted 2 days ago, led by Matthew Schofield, who's a PhD student at UCL. And so I was looking forward to show you these new results. CS is a molecule that has been studied a lot both in our own galaxy and in external galaxies, because it's always been considered a high density molecular traces for quite some time. And in this particular work, we have got 4 molecular transitions. So we're doing multi-lines of this particular molecule. And these colorful rounds, circles and squares that you see in this picture are representing the spots where we've observed the CS322. In this particular study, the resolution was not so good compared to the resolution that you can get with ALMA. It was about linearly about 35 parsecs. But we studied many spots within this galaxy, and the idea was to compare the emission of this molecule between the circumnuclear disk and the starburst rings, as well as within the circumnuclear disk and the starburst ring. And so here I'm just showing you the spectra for all the lines, for 2 to 1, the 6 to 5, 7 to 6, and the 3 to 2. But really what we found was that the CS traces, of course, both the circumnuclear disk and the rings. So there is dense gas in both of them. The starburst ring seems to be brightest in the 3 to 2. And the north arm of the emission seems to be clumpier than the south, potentially indicating higher star formation rate. But of course, the circumnuclear disks, as has been found before, is brightest in CS in general, especially in the east part and the west part compared to the AGN, so the central position of the AGN. So what's the conclusion from this particular paper, from this particular study? Well, I'm just putting up now this cartoon here of the main conclusions. And basically we found that even just with the CS, we could already have a look at the map of the temperature, the gas density, and the cosmic ray ionization rate in this region. And this was by coupling the LT analysis with the radiative transfer analysis, as well as a chemical modeling. And we found that the temperature in the circumnuclear disk increases from east to west, and that the circumnuclear disk is hotter than most spots in the starburst rings. The cosmic ray seems to follow a similar pattern, perhaps not surprising, within the circumnuclear disks, but interestingly, it was actually higher in a couple of spots in the starburst rings, again, potentially an indication of a higher star formation rate or a nice spot for episodes of star formation going on. Moving on to two different molecules now, SiO and HNCO. These are very interesting molecules from the point of view of shocks. Certainly SiO has been used in the past as a tracer of shock spattering. And so it often it traces the fast or strong shocks that are powerful enough to spatter the actual grains and not just the icy mantles on top of the dust grain. So it's Si that gets released from the cores, and then Si quickly reacts with oxygen in the gas phase to form SiO. So here in this, obviously there's a mistake there, it's to now 2027, but 2017, Kelly et al. 2017, apologies for that. So in this particular paper, we have analyzed some transitions of SiO and HNCO. Here you see the map of the 6 to 5 HNCO and the SiO 3 to 2. And what we found, interestingly, was that SiO has a strong peak in the east knot of NGC 1068 circumnuclear disk, while HNCO seems to be stronger in the west knot and weak in the east knot. So how shall we interpret these differences? Well, again, we used chemical models, and in this particular case, we ran chemical models of shocks. And without going into too much details about these plots, here is the fractional abundances of several species as a function of time. And if you could just concentrate on the blue line and the red line, you see that in the top model, where we are modeling a fast shock, SiO is certainly more abundant than HNCO, so the blue line is more abundant than the red line, while in the bottom plot, where we are modeling a shock model, at later times, HNCO surpasses SiO and is higher in abundance. And this seems to therefore indicate that the east knot, if we're right that there are that the SiO is tracing the shocks, then it's much more heavily shocked than the west knot, where maybe there are no shocks present, or in any case there would be lower velocity shocks present.
Okay, so this is your 5-minute warning.
Thank you. We only really had we have 2 transitions for each molecule, but a different spatial resolution. So we now have more ALMA data of HXCO and SIO. And here you're just literally seeing just the spectra, not properly reduced yet, but it's just really to say, watch this space if you're interested in short tracers in NGC 1068. The next molecule that I want to show you is C2H. Now, C2H is, this was a serendipitous detection here in NGC 1068. What I'm showing here is a paper led by Santiago Garcia Borrillo. And as you can see from these maps, C2H seems to be quite extended and quite intense, both in the circumnuclear disks, but also seems to trace spots in the starburst ring. Basically, again, as you can see from the spectra here of different position in the starburst rings on the top, and the outflow that arises from the AGN in the circumnuclear disks is expanding at large velocities for many parsecs. You see 3 positions there in the outflows where you can also see that the C2H is very strong. So C2H is both extended and enhanced. And again, it's brightest in the CND, in the circumnuclear disks. Now, a note here is that in our own galaxy, C2H seems to decrease from diffuse to dense gas. So it's not really a tracer of dense gas per se. And even in diffuse gas, where it's abundant, its abundance is about 10 to the minus 8 with respect to total number of hydrogen nuclei. If you look at the table here on the left, by the way, we only had 1 transition of C2H, so we clearly need more. But here, just applying a simple LTE, where for different excitation temperatures, we calculated the fractional abundances, you can see that the abundance is really high, especially when you start calculating it at temperatures that we know from other molecules this gas is at, so above 50 Kelvin. You are above 10 to the minus 7 in fractional abundance. So how do we get such high fractional abundance of C2H? Again, here I'm going to show you a model. Let me just spend a minute on these plots here. So here we are seeing 3 different chemical models computed at different conditions that you can see there at the top of each panel. So the 2 of them at a standard cosmic ionization rate. The third one, model 23, is being computed at 5,000 the cosmic ionization rate, which we think is typical of our own galaxy. The temperature goes from 100 to 200 Kelvin, and the density from 10 to the 4 to 10 to the 5 per centimeter cube. And importantly in this case, the visual extinction, so representing a sense of thickness of the gas, goes from 1 magnitude, so quite thin, translucent, to 10 magnitudes, typical of a dense core. And the gray bar there, if we concentrate on the outflow, for example, is the observational fractional abundance. And what we find is that the best matching models are really those that are mimicking a turbulent interface between the outflow and the interstellar medium, a turbulent interface that has very high densities, temperatures and radiation fields, but is short-lived, meaning that it's probably episodic. So that's why we believe it's turbulent. We found something like this only in some regions in our own galaxies, in massive outflows. And so we believe that the C2H in this particular case is actually tracing, is showing us the first evidence of turbulent dense molecular interfacing in external galaxy. And with this, I'm going to put up my conclusion on molecular characterization in galaxies. It's a busy slide, but really the main message is that you need multiple transitions of multiple species to draw strong conclusions from molecules in nearby galaxies, especially if you want to interpret ratios. you do need to couple chemical models, radiative transfer models, as well as, of course, LT considerations. And with this, I'm going to just leave you with my slides of financial acknowledgement this time, and thank you for listening.
Thank you very much, Serena, for this very interesting talk. I believe we have a few questions. So the first one is from Ann Klitsch, and she writes like this. Thank you for the nice talk, Serena. I was wondering about the NGC 1068 study. There is a hole in the center in all CS transitions, and the same hole was also present in other traces you presented. Can you comment on this, and what emission line do you expect to see all the way to the center? Thank you.
Yes, so the holes are real, first of all, in the sense that, yes, we did, maybe due to, well, we're not 100% sure, of course, but really right in the center where the AGN is, it doesn't seem to be molecular emission in those transitions that we see. Of course, in different wavelengths, you are able to see right in the center where the AGN is. We manage with the molecules, there are many papers, mainly led by Santiago Garcia Burillo, that shows right at the edge of the base of the outflow, which seems to arise from the AGN. And so I would encourage you to have a look at those very interesting papers to understand a little bit more about what's going on right in the center. Okay, and I think we, excuse me, I have one more question before we have to switch speaker. Agata Rozanska, she's writing the following. Do you take into account the interaction of those molecules with high energy photons? Do Radex and UCL Chem codes include this type of processes? We know that in many galaxies, hot phase extends up to several parsecs. Yes, so UCL Chem, yes, is a chemical model. It includes everything, includes photons, includes cosmic rays, includes X-rays, and so on. So this is, in a sense, this is a very, very good question. That when you use Radex, which is obviously radiative transfer models, you putting as inputs to the column densities of the species, your density, your temperature. But the column densities are already assuming whatever chemistry has happened before, so they don't take into account the photons per se. But UCL Chem is an ab initio chemical model, so it calculates self-consistently the chemistry. That model, as well as many other codes, of course, that are out there. I just obviously presented this one because it is the one that we use. So photons will be taken into consideration. Of course, when you look at very dense gas, you're in regions where the visualization is very high, so photons don't really penetrate apart from at the edges of the so-called the photon-dominated regions, at the edges of your clamps or your outflows, for example. But yes, they are taken into consideration. Okay, so thank you very much, Serena, and thanks for those who put in questions. If there are further questions, which I believe there are, please post them on the Slack channel. And by this, we'd like to thank you again, Serena, for a very interesting talk. And we're going to move to the next speaker, Andrea Merloni. So if you could stop sharing, Serena. Thank you. And Andrea, if you could start sharing.
Hello, yes.
Okay, very good. So Andrea Merloni will talk to us today about results from eROSITA. The eROSITA telescope provides the deepest view of the entire X-ray sky to date. In its first 182 days, it has completed a full sweep of the sky, which includes more than 1 million X-ray sources. Today, we will hear about the results from eROSITA from Andrea Merloni, who is the eROSITA senior scientist. Andrea is a staff member at MPE in Garching, and his main scientific interests are in the area of structure formation and evolution, quasars, AGN, X-ray binaries, and accretion physics. He's also involved in the eROSITA spectroscopic follow-up program, DSS5 and Foremost. Please, Andrea.
Thank you, Sofia, and good morning, everybody. It's for me a great honor and privilege to be here today with you, even remotely, to tell you about the first few months of scientific operation of eROSITA on the Spectrum Röntgen Gamma mission. And my goal, the goal for me today is to start presenting a very synthetic fact sheet about the mission and the instrument. Of course, starting with our scientific drivers, a brief history of the project and some technical characteristic and mission profile, and then move into necessarily cursory and brief, but I hope entertaining, a series of highlights about the first 9 months of science operation, both from our early science program and from the Old Sky Survey. So motivation, the main motivation for us in building eROSITA was to use clusters, X-ray detected clusters, to study cosmology. And the idea is relatively simple, at least it meant itself to be simplified by me in this talk. And this nice illustration from a quite old numerical simulation plot, more than 20 years old, from the Virgo collaboration, just illustrate the point. Here you see different snapshots that illustrate the dark matter density of a large chunk of the large-scale structure. Each row is a different cosmology. Many of these have been since clearly disproved. And each row is a different redshift, from redshift 3 to redshift 1. And you just see how qualitatively different it looks to your eye, the large-scale structure in terms of density of filaments and knots, depending on cosmology. On the bottom right here, we have a quantitative plot made a few years later by Rosati, Norman, and Borgani in a very influential review. This shows the cumulative number density of dark matter halo, of the most massive dark matter halo, as a function of redshift. And here you see different colored curves. And this is, sorry, normalized to redshift 0, okay? So at 1, it's redshift 0. And here you see how different these curves that represent different cosmologies, they evolve with redshift. Mind you, this is a logarithmic plot. So this very simple idea that I was mentioning before is that if you have a machine that can effectively and without too much contamination and biases detect and count clusters as a function of redshift as the most massive dark matter halos, then you have an exponentially sensitive tracers of the growth of structure, because these dark matter halo live in the exponentially decaying part of the mass function. And so X-rays are, of course, a good candidate for go and look for clusters, because the matter that collapse and virialize in this very deep potential wells of these gigantic large-scale structures, it's so hot that it emits copious X-rays. This was known since the beginning of X-ray astronomy. And so essentially the requirement on an instrument that would like to use clusters to study cosmology are essentially threefold. First of all, you want to be able to identify those objects in your X-ray images, because they are extended in the sky, and typically the most massive clusters have extent on the sky of about 1 arcminute out to redshift 1. So you want to be able to resolve them and distinguish it from the point source that populate your X-ray sky. And this is good because there are no many other contaminants. The other extended sources in the sky are only very few nearby large galaxies on the very local universe. But apart from that, essentially there are no contaminants. So you want to resolve the extended emission from the clusters. Of course, you want to build an instrument which is sensitive enough to detect this cluster at high redshift. So you have some lever arm, as illustrated in this plot, to compare the densities at different epochs in the history of the universe. And then, of course, you want to probe a large enough volume of the universe that gives you statistics. You want to build this mass function with good enough accuracy, and for that, you need large numbers. And early on, it was quantified in at least 100,000 objects that are needed in order to beat down these statistical errors. So, but if you want to go more detail about all the non-simplified version of the story, you can go and see the recording of a talk that Ezra Bulbul gave yesterday. And she's going to give another one later. I will mention it also. So we went then out and asked funding to the German and Russian agencies to build an instrument that could do what I just told you. And this is just one simple slide about some management aspect of the eROSITA project. It was led by Peter Predel at MP as a PI, and Paul Nandra as the director of the energy group, share with Peter most of the mission level management. And Rashid Sunyaev instead was the lead scientist of SRG in Russia. And in Germany, eROSITA was built with funding from the German Space Agency, DLR, and the Max Planck Society, with a relatively small group of institutes participating in this endeavor, at least small for space missions of this caliber and size. And here I just want to stress that at MPE, the Science Lead Institute, of which I am, and I'm working as project scientist for this mission, we did the lion's share of the work that went from designing the instrument, manufacturing most of the parts, doing all the integration of all the elements of the telescope, doing the testing, and now we are doing data handling, processing, and archive. So you can imagine for a single institute, even as big as MPE is, this is a tremendous effort. So here are a few pictures of the hardware that we built over 12 years. This is now the 2 telescopes that are part of the Spectrum Röntgen Gamma mission. eROSITA is by far the largest and more sensitive one. You see this on top, this hexagonal structure here with this protective cover. And ARTEC-C is another X-ray telescope that works at higher energies and that is observing the sky in the same direction as eROSITA. And these 2 coaxial telescopes are mounted in this picture on the platform that provide the power. Here you see the solar panels and also communication in order to downlink the data to Earth. And in this picture was taken at Baikonur just a few days before launch, when the payload was already integrated on the upper stage and brought it into its L2 orbit. Now a bit more detail about eROSITA itself. Now I have pictures that were taken without the protective cover in the integration lab at MPE, maybe 4 years ago or so. On the left, you see the mirror system. So eROSITA is not a single telescope. It's an array of 7 identical telescopes. They inherit XMM lightweight mirror replica technology. And as XMM, they have similar performances in terms of spatial resolution. So the on-axis alpha energy width is about 18 arcsecond, which correspond to PSF full width of maximum of maybe 10 to 15 arcsecond. What matters, of course, is the field of view average performance, because as I was showing in this plot, this is a PSF mapping that we did in our lab. You see that the image is well focused at the center in the optical axis, but this is typical of X-ray telescope Volter design. It gets this very bad butterfly degradation as you move towards the edge of the field of view. So the field of view average PSF is worse than the non-axis one, of course. It's about 26 arcsecond. But overall, this is sufficient to resolve these 1 arc minute clusters. And in fact, they give us positional accuracy for point sources to better than 5 arcsecond, typically between 3 and 4 arcsecond. So it's quite good optical design. Here on the right, you see instead the focal plane. The 7 mirrors focus the X-rays on 7 cameras. These are the 7 electronic boxes that you see associated with each camera, and this very complex array of tubes and harness of cables, and it's a kind of a nightmare to build. But the main point about the cameras is that they are an evolution, an improvement of the very successful PN CCD that has been working with for XMM for more than 20 years. Some of the improvements was to build a frame store so that you don't have out-of-time events. There are no chip gaps. Then this is 1 camera flat if you want. It's very uniform. There are no bad pixels. There are no, as I said, chip gaps. So you expose the entire field of view with this very uniform detector and very little temperature dependence. All in all, this is almost a factor of 2 improvement with respect to XMM in terms of spectral resolution. For the non-X-ray astronomers here in the audience, I would like to remember that when we build X-ray images, we do almost at the same, we do like an IFU at the same time, because we can measure the photon of the energy of each individual photon. So for each photon detection, we can measure energy with typically a few % precision, or 1 EV resolution at 1.5 keV, like a Grism spectroscopy if you want. So I mentioned about the spatial resolution. I told you we needed to be sensitive, and this is an illustration of that. This is the effective area. So the photon collecting power of eROSITA in red for the 7 telescope combined, compared to the flagship X-ray telescope that are working today. XMM Newton, which is the largest in operation. When you combine the 3 detectors together, you get this blue dashed curve. So you see that in the energy range between 0.3 and 2 keV, which is the energy range where most of the 10 to the 7 ISM from cluster emits, eROSITA is as big as XMM. So it's essentially, we build the biggest in terms of the collecting area something comparable with the biggest X-ray telescope working today. The other point was, as I told you, to probe large volumes, and for that, the advantage that eROSITA has compared to XMM, Newton, and Chandra is this very large field of view that you can see here. So this translates into a grasp, which is a survey speed metric, which is the product of the field of view times the sensitivity, which is a factor of 5 better than XMM and 100 times better than Chandra as it is today due to the degradation of the CCDs. And so we build a large, fast survey machine, but we still need to cover the whole sky to get enough volume to detect these 100,000 clusters. And we can do that by using our telescope instead of point and stare mode in this scanning mode. We can, as I will show you in a minute, we do scanning throughout the whole sky survey, but we can also do raster scan to cover rectangular areas up to 150 square degrees of any given depth by just changing the speed with which we scan. And this gives a very nice large field images that it was not possible to do in X-ray astronomy before. So here we are now. We put all this precious hardware in the fairing on top of this cylinder full of combustible. It was a very scary time, but the launch was flawless. The Proton rocket from Roscosmos delivered beautifully textbook launch in this very large orbit around the L2 as planned. So this is a picture of the orbit of SRG around the L2 point. It's very large, but this is what it was designed for. Just, I don't have time to go to the details of operation, just to mention that operations are done with Russian ground segment and are coordinated by mission control in Moscow by the Lavochkin company in close collaboration with the IKI, which is a Russian Academy of Science Space Institute. And the extra level of complication is that eROSITA is actually commanded by MPE, not by Mission Control Center. And so there is a three-way communication that we had to sort out between MPE, Mission Control Center room that you see here in the middle, with IKI. That's a picture taken at IKI a few days after launch with our team and their team working together. And then eventually with the Mission Control Center in Lavochkin, which is pictured here on the left. And I have to say, despite the complication, everything has been working very well since the beginning, thanks to the dedication of the people. And in particular, I want to really make a shout out to the people at MPE, likewise in Moscow, that have been working, had to port all this complex operation scheme working from home since the COVID pandemic strike, both in Munich and in Moscow. But we didn't suffer from that in the sense we could continue operation, and we are continuing operation since. Okay, so now I am now in the position to show you some highlights from starting from our early science program. If you want to read a bit more, we wrote a Nature Astronomy comment article maybe a couple of months ago. But here are just 4 nice pictures, all wide field images of deep exposure that we took during our performance verification phase in October and November. On the top left is a cluster of galaxy with quite disturbed emission. Is probably a cluster which underwent merger or strong effect, feedback effect on the central AGN. So you see the diffuse emission from the cluster distorted and clearly non-spherical and non-uniform. On the right is a beautiful image of one of the brightest supernova remnants in the sky. This is actually an X-ray color, false color image taken between, I think, 0.5 and 4 keV. So the blue is the harder energy and redder is the lower energy. This is Papis A, a supernova remnant nearby the Vela. And here is another extragalactic field that was part of our first release. This is a system of interacting clusters of galaxies. I will refer you to a talk by Thomas Reiprich later today that will go into much more fantastic detail about this observation. And here on the bottom right, it's our first light image. At the center, there is supernova 1987A in the Large Magellanic Cloud. And you see fantastic detail about the hot interstellar medium of the LMC. One thing I want to highlight here is that this bright source at the center allowed us to take a spectrum of the supernova remnant. And here is a comparison of the eROSITA CCD spectrum in cyan versus the XMM Newton PN spectrum. This was done before our calibration. So don't worry too much about the cross calibration yet, but just this spectrum is supposed to emphasize the advantage in spectral resolution that eROSITA has and allow you to much more clearly resolve emission lines. The largest investment of time during our performance verification phase in November was spent on an extragalactic field. We covered in 4 days about 140 square degrees, and the idea here was to go at the depth that we would like to cover the whole sky at the end of the whole sky survey. That will take us 4 years. So this is, in a way, the idea of how the X-ray sky will look like eventually when we have completed our survey program. And this was very useful, of course, for us to test our pipelines. For example, how good are we at detecting extended sources? We detect more than 400 galaxy clusters. And because we put this field in an area with very good multi-wavelength information, we could already identify and measure spectroscopic and photometric redshift for a very large majority of these clusters. And they extend from redshift 0.1 to 1.1, which is exactly what we need to do our cosmology, as I told you. But if you want to know more about this observation, you should also go to the next talk by Ezra, which is tomorrow. Of course, this image does not only contain extended sources. Actually, most of the white dots you see are distant AGN. We detected more than 25,000 point sources. So just by the sheer number of objects detected, this 4 days worth of eROSITA observation constitute the largest contiguous X-ray surveys ever done. 85% of these point sources are AGN, typical redshift about 1. 15% are stars in the Milky Way that emit through magnetic corona. And there is a lot of interesting science to be done by studying the population of coronally active stars detected in X-rays. So we did this early observation, and we are now analyzing them, writing papers that hopefully will appear in a few weeks and months, the first ones. But then in December, we started the All-Sky Survey, and this is an illustration of how it works. I don't know how the movie looked like for you, but you see here the telescope, the SRG telescope rotating. It's a slow rotator. So what we do, we don't point at stars, as I told you, but we let the instrument scan. In 4 hours, it does a great circle. And in 1 day, you advance by exactly 1 field of view, which is 1 degree wide. So in 180 days, you cover the whole sky by just combining all these great circles. And here on the right, you see how this all great circle intersect at the ecliptic poles, because we keep our rotation axis fixed. And here you see an animation of actually this is a real data as they cumulate in the area around the south ecliptic poles. You see the rotation of the scanning axis and the source accumulating in the area around them. And you see that slowly, as I told you, in 6 weeks, we complete an all-sky survey. And the plan is to do it for 8 times for 4 years. That will give us the desired sensitivity to detect many high redshift clusters. And after this 4-year program of all-sky surveys, we will have, at least right now, funded 2.5 more years of pointed observation that will include the possibility for the community to apply for getting eROSITA time. So the All-Sky Survey, as I told you, is complete. I'm sorry. Okay, a few numbers about the All-Sky Survey. As I told you, it takes 6 months. We started on December 13, so it was completed on June 11. The sky exposure is shallow. It's short. It's only 200 seconds worth of exposure over most of the sky. As I shown you at the ecliptic pole, this goes up because they are revisited almost daily. Actually, at the ecliptic pole, we have deep exposure up to 36 kiloseconds with fantastic data about variability of the X-ray sources there. The good news about background at L2 that we've discovered, because we are the first mission operating X-rays at L2, is the background, despite being a bit high, and this is consistent with the model of the solar cycle, it's very stable. We did essentially not detect strong background flares. That means we didn't have to throw away data. In this way, we could cover the entire sky without gaps. And this is also helped by the fact that we have a relatively flexible mission planning. There was one instance in which we have to put the telescope in safe mode in mid-February. So we lost almost 48 hours of data, but we could essentially reorient the scanning axis so that to cover that gap at the expense of some depth in the area. So if you want to know, we detected about 400 million well-calibrated photons in the energy range, which is not background dominated, between 0.12 kiloelectron volt and 5 kiloelectron volt. And when we apply our preliminary source detection, we detect more than 1 million sources over the Earth sky, of which about 80% are AGN, 20% are Milky Way stars. And this number by itself is as much as the total number of sources that all previous X-ray missions had accumulated over 50, 60 years of history of astronomy. So a huge discovery space is opening up now.
So Andrea, this is your 5-minute warning.
Perfect, thank you. And so we detected 20,000 clusters up to redshift 1, so we are in good shape for doing cluster cosmology. And of course, we have also detected numerous transients. So I hope you have a big enough screen, and if you don't, you can switch to full screen mode, because I'm showing you now the full sky image of the eROSITA All Sky Survey. This was taken, I mean, the original image can place photons into 4 arcsecond pixel. Considering our PSF, this has a dynamic range, the original image of more than a billion, so 10 to the 9. Of course, this particular image you see was smoothed in order for you to appreciate more the extended structures. And it was color coded according to the energy of the photons in the sensitive energy range between 0.3 and 2.3 keV. So red are photons between 300 and 600 electron volts. Green are photons between 600 electron volts and 1 kilo electron volt, and then blue are photons above. This is a galactic projection, so the Milky Way is horizontal here, the galactic center is at the center, and of course the dust and the material in the Milky Way absorb the soft X-ray, so you only see the blue stuff coming out, the higher energy photons coming out along the galactic plane. But you see how rich in structure this image is. Most of the red that you see at high latitude is probably 10 to the 6 Kelvin local gas, the so-called local hot bubble, very close to the solar system. But as you move toward higher energy in yellow and green, you start seeing the effect of dramatic feedback events from supernova remnants. The X-ray sky is quite peculiar. It's maybe different from what you're used if you're, say, an optical radio astronomer. You see things which are very nearby, like the supernova remnants. Vela is this very large structure here on the right. There are many other beautiful supernova remnants that appear very bright. Of course, there are famous X-ray binaries, like Scorpius X1 was the first source detected in X-ray astronomy by Giacconi in '62, and Cygnus X1 here, this famous source, the first black hole, confirmed black hole X-ray binary. It was the object of a famous bet between Kip Thorne and Stephen Hawking about the nature of this source. But interestingly enough, if you look in the extragalactic sky, you see also clusters of galaxies like Virgo, Coma, and superclusters like Shapley as you start moving away to a few hundreds of megaparsec. And in fact, if you look closely, I can assure you there is also one dot here among the many that you see in this smoothed image, which is a redshift 3 quasar, all in the same image. You go from few parsec away from you to redshift 3. And here, just in 1 minute, a few highlights that we published with our press release. You can go through the MP side. This is the actual All Sky Survey image of Vela supernova remnant. This very large structure. There is the Puppis supernova remnant, which is more distant. That's why it appears smaller, and it's younger, more luminous. And here there is a hard, in blue, you see a circle, which is another more distant supernova remnant, which is mainly non-thermal. This is now the Large Magellanic Cloud. In this circle, there is the first light image, but with the All Sky Survey, we are now able to probe the entire size, the entire face of the Large Magellanic Cloud, and probe not only sources within the Magellanic Cloud, but also the ISM of the Magellanic Cloud. And this is a very nice serendipitous discovery. This circle that you see here is the dust echo of the outburst of an X-ray binary that happened in February 2019, which is still visible at the center of this image. It's now much fainter than it was a year and a half ago. And here you see essentially the reprocessing, the scattering of the X-ray emission on dust lanes along the line of sight. And by modeling that, you can measure the distance to the source. And so one last thing before I close, if I go again to the full color image, if you look above 1 keV, most of the soft diffuse emission from the galaxy fades away. At 1 to 2 keV, most of the X-ray background is dominated by a celestial source in so-called cosmic X-ray background. And here you see the many AGN and clusters more clearly highlighted. And here, but just for fun, you can plot galaxies, nearby galaxies. This is the 2 mass redshift surveys within 88 megaparsecs. And just with your eyes, you can essentially associate one-to-one the presence of the X-ray structure with the galaxy redshift structure. And you know, this is the full 2 mass redshift coverage up to maybe 200-300 megaparsecs. And essentially you can identify most of these famous large structure and superclusters directly in the eROSITA image, which I find really cool. So my final slide is this one. I emphasize how simple the scientific motivation of eROSITA was, cluster cosmology, but behind that, as you can imagine, when you push your instrument to the boundaries, you end up with legacy value of data set that I hope will keep astronomers busy for many years. So beyond detecting all more clusters more massive than 2 × 10⁻⁴ solar masses along our past light cone, we will detect millions of AGN with typical redshift of around 1 and X-ray luminosity in 10⁴ X per second. But as you can imagine, a lot of interesting study will be done by looking at population study of compact objects in the Milky Way, of the stellar population of the young magnetically active coronal stars in the Milky Way, plus of course the dynamical view of the X-ray sky. Thanks to our scanning strategy, we'll be able to detect many transients, including hundreds, if not thousands, of tidal disruption events, and hopefully more of this serendipitous discovery of things that we didn't expect. So one word to close about the data release policy. This, as you may know, the eROSITA data are shared by 2 teams, one in Germany, one in Russia. So what I'm telling you now refers to the German team data, proprietary data. So the performance verification and calibration will be released after 1 year in early 2021. This will include this IFET's beautiful survey. The All Sky survey data have a proprietary period of 2 years. So the ERAS one that you just saw will become public 2 years from now. And then we have a plan to do 2 more data releases of the first 4 and then the full 8 All Sky survey data sets in 3 installments. And as I told you, then we will open the usage of Sargini eROSITA to the community. So I close here by thanking you and also taking this opportunity to put up a hopefully complete, but I'm sure not so complete, list of all the people that over the years have contributed to make this science possible. Thank you.
Thank you very much, Andrea, for this exciting talk. So we have a few questions for you. We start with Alison Mitchell. Lovely results with eROSITA. This number of sources, 1 million, from the All Sky survey is using a point source analysis pipeline, AGN/stars ? Is there already an estimated total number of extended sources detected?
Yes. So one source, 1 million, contains both the extended and the point-like. But of course, the vast majority of point-like, I think I was too fast. We detect, I think, out of this 1 million, about 2% are clusters that are detected as extended. So we have already detected 1/5 of our final goal in terms of number density of clusters, the number of clusters that we need to do our cosmology experiment.
Thank you. And then we have also a question from Kiro Pinto. Spectacular results. Thanks a lot, Andrea, for the great review. I was wondering if there is a sort of daily/weekly automatic calibration performed in order to account for slightly different solar foreground and other effects altering the conditions of the CCD detectors, or these have been remarkably stable over the months you've been doing the observations?
Things have been stable, remarkably stable, I have to say, but we do monitor that. So we have a few ways of doing that. As I told you, we go over the same area in the sky that it poles every day, so we can do a very simple check of how the background look like. But on top of that, because we have 7 cameras and 7 detectors, we can put for about half an hour every day, one of these 7 cameras, we close the filter and we measure the particle background from the instrument. And we can do rotating, and in this way we lose, you know, a fraction of a % of the data, but essentially we can keep monitoring the background.
Okay, thank you very much. Thanks very much, Andrea. And I think it's time that we move on to the next talk, which is a prize talk.
Thank you. And keep your question coming on the Slack channel if you want.
Yes, please. Those who didn't get the chance to get answered now, please put them in the Slack or things that you think about as you go. So, Stefano, Vitale, it's my pleasure to introduce this year's Tycho Brahe medal, which is given by the European Astronomical Society. This medal is awarded to Professor Stefano Vitale from University of Trento in Italy this year. He gets the medal for leading the science, I quote, for leading the LISA Pathfinder mission, which has demonstrated with extraordinary precision the technology required for the future laser interferometry space antenna, whose fundamental aim is to observe low-frequency gravitational waves from space. So Professor Vitale studied at the University of Rome, but from 1994 he's a full professor at the University of Trento. After starting out in condensed matter physics, his interests turned to general relativity and the possibilities to observe gravitational waves. Since 2003, he is the PA of the LISA technology package payload on board the ESA ESA Pathfinder mission. And since 2017, he's also the chair of the Science Program Committee of ESA. So today, in his prize talk, he will tell us about LISA and LISA Pathfinder. Thank you. Or please, I should say. Thank you and please.
Thank you very much, and good afternoon, everyone. Let me first thank so much the Society for this great honor. I should share this medal with many colleagues, and I'll get back to that at the end of the talk. This is a talk on LISA and LISA Pathfinder. As you may know, LISA is a gravitational wave detector aiming at frequency between a few tenths of microhertz and a fraction of a hertz. This is a frequency range you cannot access from ground because of the gravitational noise due to the motion of the Earth's surface and the atmosphere. An easy way to illustrate the strong observational interest in this frequency range is to make reference to a standard source made of two bodies of comparable mass. The dynamics of such a source is nearly Keplerian till a very late stage of its evolution. And the frequency of the radiated wave is just twice the frequency of revolution. So you can use Kepler formula to calculate the frequency of the wave, and that depends only on the mass of the system and the separation of the two bodies. Now, as for the separation, you know that when this separation approaches the sum of the two Schwarzschild radii of the body, you're getting into the final merger and the source is going to disappear as a gravitational wave source. And so you better normalize this separation to this sort of minimum distance so that this normalized separation, in a sense, measure how far are you from the final merger. And if you do that, the frequency now becomes a decreasing function of the mass and a decreasing function of this normalized separation. So now you immediately get what you achieve by punching through this terrestrial gravity noise. On one side, you access a much larger range of masses, let's say 1 million solar mass, plus or minus an order of magnitude. This is the realm of supermassive black hole in all their incarnations, from the capture of a small body from a supermassive black hole. This is an exquisite general relativity laboratory, to the collision of two supermassive black holes with their own galaxies. Actually, this source is likely to be one of the most powerful sources we are ever going to detect. The reason is that the amplitude of the gravitational wave is proportional to the product of the two masses. And basically, you calculate that a system like that, in a detector like LISA, has signal-to-noise ratio in excess of hundreds at any redshift, even at redshift of 20 or more. And you see here a simulation of raw LISA data for one of these events at a redshift of 15. The opposite end of this frequency range is a range of sources that are so much separated that for some of them, the final merger is in the infinite future. So this, in a sense, is our only chance to do non-transient gravitational wave astronomy. We are talking mostly, these are galactic sources. They must be nearby because they're not very powerful. And we're talking mostly white dwarf binaries, but any binary would do. As was mentioned yesterday in the plenary of yesterday, even LIGO Virgo black holes have spent a year or more in the LISA band before getting into the audio band of the ground-based detector. The name of the game here is abundance. These sources are very abundant, and thanks to the yearly integration time of LISA, you get a pretty high frequency resolution. So the people calculate that we should be able to discriminate tens of thousands of these sources in the data of LISA. And this is an impressive census of this kind of sources in the Milky Way, to be complemented and to complement similar census that you do in the electromagnetic with Gaia or LSST. We will not be able to discriminate them all. Some will form a stochastic foreground. This is, in a sense, a bit of a limitation for LISA as an instrument, but this is also an interesting source in itself. And because this is a Tycho Brahe medal, you may be curious to know that the nova stella of Tycho Brahe, 1570, supernova 1572, might well have been one of the LISA sources at some stage of its evolution. Now, before I move to LISA Pathfinder, let me give a closer look to LISA as an instrument. As you know, this is made of 3 satellites that orbit freely around the sun at about an astronomical unit. And because of one of these miracles of celestial mechanics, they form a pretty stable triangular formation. The spacecraft sends beam and exchange beams with the other. Each spacecraft exchange beams with the other 2. In particular, it sends a beam to the other 2 spacecraft and receives 2 beams from the other 2 spacecraft. And the basic instrumental element of LISA is this one, is one spacecraft sending a light beam to a receiving spacecraft where the frequency of the received beam is measured. Now it turns that if you propagate an electromagnetic beam through the curvature of the gravitational wave, it accumulates a frequency shift along the way. And this frequency shift is directly proportional to the metric tensor, so what the people consider the gravitational wave signal. Still, because of the curvature, the frequency of the beam is also modulated in time. I don't know if you can see this cartoon where the color changes in time, and actually it is the time derivative of the frequency which is proportional to the curvature tensor, to the Riemann tensor in a sense, is the real signal of LISA. Now, unfortunately, as you know, there are much more mundane ways of producing a time-varying frequency shift. One way is that you move either the emitter or the receiver or both. If the velocity changes in time, because of the standard Doppler effect, you have a non-zero time derivative of the frequency, which is simply proportional to the relative acceleration, to the difference of acceleration of the 2 satellites relative to the local inertial frame. And unfortunately, if you put satellites at 1 astronomical unit from the sun, the solar radiation pressure is so noisy and so strong that would impress to this satellite acceleration that would mask and cover any astrophysical meaningful signal. So the way around this problem since the early days of LISA has been, okay, carry inside each spacecraft a free test mass that you use as your inertial reference. This is floating inside the spacecraft like an astronaut in the International Space Station. There is millimeter clearance all around the test mass. Obviously, the spacecraft keep taking the hit of the solar radiation pressure. And so you have to do something to avoid collision. You measure where the spacecraft is, and using the propulsion and the spacecraft propulsion, you adjust the position of test mass to stay centered, of the spacecraft, sorry, to stay centered on the test mass. Now you have a good reference because the test mass is shielded from the solar radiation pressure, so it's a good inertial reference. So you can measure the acceleration of the spacecraft relative to this inertial frame and correct your signal for that and cancel the effect. Unfortunately, you don't cancel everything because the test mass could accelerate themselves if there is any parasitic force, molecules hitting the test mass, electromagnetic and whatever, that accelerate the test mass relative to the inertial frame, then you get a modulated frequency shift, and you cannot distinguish between gravitational wave and the acceleration of the test mass. And in a sense, this is one of the dominating entry in the noise of LISA, and in a sense, it's the subject of the rest of my talk. It is not the only entry in the noise budget of LISA. When you measure frequency with an interferometer, interferometers are noisy, so you're making noise with your interferometer, and I call this the interferometer noise. And now if you look at one of the LISA sensitivity curve, this is the red line, is the LISA projected sensitivity curve. This is an amplitude spectral density of metric tensor measurement. It turns that at the lower frequency, you're entirely dominated by these test masses trying to accelerate relative to the inertial frame. At only above some tens of milliards, the interferometer sets your limits. Now remember, LISA is a low frequency experiment, so it's not surprising that most of the signal to noise ratio on most of the sources for LISA is accumulated exactly in the frequency range where you're dominated by the acceleration of the test mass. So these must be very, very low. And how low is in this picture here. This is the requirement for LISA of difference of acceleration between two test masses. Is an amplitude spectral density. Don't care too much about the requirement. You have to be below this noise, right? So you have to be below this line. Now look at the scale. These are meter per second square. So 1G in this plot is 10. So that's why LISA requirements are called sub-femto G force suppression requirement. You need to suppress forces at sub-femto G. Now, nobody came up with a good idea to demonstrate that this is possible at all on ground because of the 1G that dominates everything. And all space missions that needed inertial test masses have much more relaxed requirement. And actually, when LISA came to the system, the only one in view was GRACE, where you can see the requirements are relaxed by probably 6 orders of magnitude relative to what LISA needs. So it's not surprising that as soon as ESA decided that gravitational wave astronomy was something to go into because of its great importance, they concluded that they needed to test if it is possible to put test masses in such a pure geodesic motion. They needed a test in space. And so they devoted a technological mission that at the time was called SMART 2 and then became LISA Pathfinder. And the concept of LISA Pathfinder is very simple: to demonstrate that the relative acceleration of two test masses is not larger than something. You don't need them to be separated by 1,000,000 kilometers apart. So you can, in a sense, squeeze 1,000,000 kilometer arm of LISA and put it into a single spacecraft. And that's what LISA Pathfinder is two test masses inside a single spacecraft. You have an interferometer to measure their differential acceleration or the difference of acceleration. You also have to carry an interferometer to measure where the one of the test masses is to implement this drag-free technique where the satellite follow the test mass. Unfortunately, in LISA, you can follow each test mass with a separated satellite. Each one is in one different satellite. Here they are both in the same satellite, so you cannot follow them at the same time. And so unfortunately, we are forced to apply a little force to the second test mass to avoid it to drift away. We pay a price in terms of noise, I'll tell you later, and we have to correct the data not to underestimate the acceleration. So this is the instrument. 2 gold platinum test mass, 2 kilos each, very pure, very non-magnetic, and then interferometer and a set of interferometers sitting on a high stability 0-dur optical bench. The test masses are surrounded by electrodes. They don't touch them, right? They are millimeter all around. These electrodes are needed to give the force in LISA Pathfinder, but it's also needed to give forces along degrees of freedom along which you don't do the gravitational measurement in LISA. So this instrument will fly on LISA exactly as will flew it on LISA Pathfinder. There are other accessories you have to carry with you. For instance, the test masses keep charging up because of the cosmic rays. You cannot use a grounding wire to discharge them. So we take with us ultraviolet light, we generate photoelectron, and we steer them to neutralize the test mass in a proper way. And there are even more complications that you have to face. You have to block the test mass, otherwise rattling for a millimeter at launch will damage completely your spacecraft, and you have to enclose everything in a vacuum enclosure to handle the vacuum on ground. And so all this complement fits into a cylindrical box that fits into a satellite that was entirely dedicated to this experiment. And if you want to see the real hardware, this is the gold platinum test mass. This is around the sun somewhere now. It fits into the electrode housing, the box with the electrodes, and everything is fit into this big vacuum enclosure with all these accessories. By the way, this is still an optical system. The test masses are end mirrors of an interferometer, so everything must be aligned to microns and submillirad, and the industry made a fantastic job here. And that's the optical bench. This is built with a technique called silica bonding. You bond together a 0-dur component, and the technique, when the bond is cured, You cannot distinguish them. There is no physical property in the bonded material that is distinguishable from the bulk, which is very important for the stability. The price you pay is that you get a minute to align things to micron and so millirad. And if you make it wrong, you have to throw out everything. But they didn't do that wrong. It was fantastic. And here you see the optical bench equipped with all diodes and all components. Zero-Dur holds everything together. You see here the two complement, the two test masses with accessory held together with Zero-Dur. Very complicated instrument, and again, it goes to the credit of industries and institute that work to that everything worked flawlessly, as I'll tell you later. You see it being integrated in this cylindrical box, and here you see the cylindrical box being integrated in the satellite with its propulsion module being integrated in the fairing of a Vega launcher. And we launched it at the end of, in December 2015. Then we had to navigate a month or so to go to L1. Unfortunately, low Earth orbit are gravitationally too noisy for this experiment. And so we went into a Lissajous orbit around the L1 point of the Earth Sun system. So what we had to get and what we have achieved. So this is the same plot as before. These are the LISA difference of acceleration requirement. Is noise, so you have to be below here, so you have to be outside the gray area. But ESA said, well, we know that your system is more noisy, so we were happy if you can get within a factor 10 from the LISA requirement. We are sure that from what we learned from your mission, we will be able to extrapolate to LISA. Even more important, they say we don't want to spend long hours testing at very, very low frequency, so we will be happy if you demonstrate things above a millihertz, and again, we will extrapolate to lower frequency based on what you measure. So this is what we were requested to do, be outside the blue area. And what were we expecting to do? Well, the noise budget for LISA Pathfinder is a book, and this is the front page of the book, but it turns that two entries we were expecting to dominate the noise much. One is this unfortunate things that we have to push a little bit the second test mass to keep it in the spacecraft. Now we do this electrically, and you generate electric field with a voltage generator. Voltage generators are noisy, and this noise gets directly converted into a force noise. Now it turns that the larger the force you want to counteract, the larger the noise you're doing for a given voltage generator. The second effect is more intrinsic, is Brownian noise due to the collision of the test mass with the residual molecule of the gas. We are low pressure, but we have some molecule. This effect scales with the number of molecules, and so scales with the pressure. The lower the pressure, the better off you are. And so we calculated what we were expecting in this plot. And so we were expecting that our voltage noise would limit us at low frequency on this line, the Brownian noise at a higher frequency. And then as in LISA, we are limited at high frequency where it matters less by the interferometer noise. We had a fantastic picometer per root hertz interferometer, same class as the one you need in LISA. And so the convolution of the three lines is this line here. And as soon as we went into operation March 1st, we were at low frequency, we were bang on the line. At a higher frequency, we were much below the line. And the reason for that is that the interferometer in space performed close to the intrinsic limit, while on ground, we could only demonstrate the picometer that we needed. So we were close to prediction and definitely better than requirement. So we were happy. But at low frequency, you see, we were limited by this force noise. And so we were asking why we have to apply so much force noise. The reason why we have to apply force noise to start with is basically because this big chunk of material here attracts gravitationally this test mass and vice versa. So you have to, if you try to compensate that with electrical field, no way, that's too noisy. So we do a two-step approach. First, we try to balance the gravitational field by putting a large tungsten mass on the other side. We have to calculate the field, we can't measure it. So we take note of position and masses of all elements of the satellite down to the screw level. And we balance to 0, but obviously it's a 0 plus or minus something. And so the name of the game is assessing what is this plus or minus. So you have to calculate all the errors you can do in installing all components, including screws. And so our conclusion was that we should have been able to balance the gravitational field to 65 pico-G, right?
No, this is your 5-minute warning.
Okay, thank you. So this is 3 sigma, a lot of margin, but it was 65 pico-G. But when we went up in orbit, we discovered that we had balanced to 2 pico-G. That's partly because of the margin, partly because of luck, I must say. You need luck in life. And so we rushed back to the instrument and say, oh, we can crank down the force. And as soon as we did that, the noise went down basically at the LISA requirement. And so we were very happy. Notice that in the meanwhile, even the Brownian noise, which is this plateau here, went down. And this is not because we did anything, but because the system is vented to space and the pressure keeps going down. And so when we achieved this result, we hit the front page of Physical Review Letters. We got some media coverage, even if we were during the media coverage of the LIGO and Virgo fantastic results. And while we were celebrating these results, the pressure kept going down because we were pumping. This is the Brownian noise as a function of time. And so by the end of the mission, our results were so much below the LISA requirement with margin all over the place that I think we now know that we could do LISA. LISA Pathfinder, to be honest, is not just that. We did many experiments dedicated to single effect that we want to understand to design LISA. Each experiment produces one of these papers. I can give you one example. For instance, we measured the charging of the test mass because of the cosmic ray. We found a reasonable good agreement with the simulation that had been made using JN4 and these other high energy simulation tools. We also discovered something. We discovered low energy electrons that could not be predicted by these high energy tools, but I have no time to go into details, so please read these papers. But obviously the main result we got is that ESA said, okay, let's go. And so in mid-2017, LISA was selected as the 3rd large mission of the Cosmic Vision program of ESA. Since then, is steadily advancing, is now in phase A, with no major problem. And so ESA is pretty confident to be able to adopt the mission by the end of 2023 or 2024. This mission adoption is a milestone after which you start cutting the big metal and spending the big money. After that, predictions are more difficult. Tomorrow you have a full presentation by the Director of Science, Gunther Hasinger, so he is much more qualified than me to predict the launch date and the operation date for LISA. And so before I finish, let me go back to the question of who really owns this medal. Let me tell you that this mission has been made possible by a team of clever, ingenious, and resilient students, postdoc, scientists, engineers, and managers from institute, space agencies, and space industry alike. They really believed in the project, and they worked enthusiastically as a team of peers. And because of that, they could endure and overcome an incredible series of hurdles and difficulties. So working with them, I must say sincerely, has been one of the greatest privileges of my life. So before I thank you for your kind attention, let me thank them again for this incredible achievement. Thank you.
Okay, thank you very much, Stefano, for a great talk and very interesting science. So we have time for some questions, and we have one question up there already from John Murrell. He wonders if you could use LISA Pathfinder technology to get a better value for the universal gravitational constant.
Very good question. We struggle with this. Unfortunately not. We measured big G with 2 digits, right? This is not an experiment. We didn't have the proper testing source, and the instrument was not done for that. So we tried to do our best, but in reality we did not. And actually, honestly, I don't see why in space the gravitational constant should be different. The planet would have different trajectories, right? So, but the answer, no. The short answer is no, we didn't.
Yeah. Then we have Eva Laplace, and she's asking, or she's starting by saying, congratulations on the prize, and thanks for this beautiful overview of the LISA and LISA Pathfinder missions. And then she asks, could the very large number of gravitational wave sources lead to interference effects? How will LISA deal with this?
Carefully, as we say. Yes, as I told you, it's mostly the galactic binaries will definitely form a foreground, right? And certainly the data analysis in LISA is one of the major challenges, and it's very interesting. The big sources, no problem. But when you dig, the abundance is such that when you dig to lower and lower signal to noise ratio, ambiguity will be the name of the game, and you will be able only to do this Bayesian prediction on the possible scenarios. So that depends on the detail. It will be refined. People are working since years and will work for at least another 10 years to improve this method. So join the community by all means.
Okay, I don't see any further questions coming up. However, I have two congratulations. One from Günther Hasinger, the Director for Science at ESA. Congratulations to Stefano for this fantastic achievement. And one from Roger Davis, the EAS President. Many congratulations, Stefano, and the whole team on the award of the Tycho Brahe Medal. And I would like to join them both to congratulate you and your team behind LISA and LISA Pathfinder. And thanks all the speakers for this session, this plenary session. And I believe all the talks will be available for later consumption if you hadn't had time to listen to all of them now. And also please remember the Slack channel where there is a lot of questions, answers, comments, and discussions going on from all of the talks in this plenary. So thank you all very much again to all the speakers, and thanks to the audience. Goodbye.